Good morning, Further Maths. We are looking at Fermat's little theorem again today, looking at some more algebraic questions, and also we're going to look at the proof. But firstly, we're going to look and see how it can be used to test for prime numbers. Just a reminder of his little theorem up there, that the second version, the one where if we've got HCF, A and P being equal to 1 and P is prime, then we have this result here. A to the power of P minus 1 is congruent to 1 mod P. So let's use Fermat's little theorem to test whether 7 is prime. So we know that 7 is prime. But what, of course, we would do is we would pop that into there. So test with A equals 2. You could, of course, test with other values of A, but if we stick to 2 because it's the simplest one to deal with, we would work out 2 to the power of 7 minus 1, 2 to the power of 6 mod 7, 2 to the power of 6, 32 is 5, it's going to be 64. So that is equal to 64 mod 7. And of course, we know that 63 is a multiple of 7, so that's congruent to 1 mod 7. So yes, that checks out with Fermat's little theorem, so 7 is prime. Now, when you're first kind of starting out, of course 9, oh, 9's tricky, you think all odd numbers are primes. So let's put that into Fermat's little theorem and see if 9 is prime. If you don't remember, you can always just put it into Fermat's little theorem and see what happens. That's 2 to the power of 8. And so that's going to be double that, a couple of times more, 256. And of course, if I subtract 180, if I subtract, I don't know, 56, I'm on 26. So is that 1 to 4? You know what, I don't know. I could use my, I've got my button here. Mod, what am I doing? 256, comment 9, 4, yes. So that is congruent to 4 mod 9. So obviously that's not congruent to 1 mod 9. So 9 isn't prime. Okay, so that's all very well for kind of little ones, but a couple here, and I advise you just to pause and work through these. So there are two questions. Firstly, is 51 prime? You probably know whether 51 is prime or not, but there's, possibly a, slightly questionable one. Just to give you a little hint at how to deal with those powers, because I appreciate finding 2 to the power of 50 is a bit more awkward than finding 2 to the power of 8 and 2 to the power of 6. And then 341. So if you pause the video, try and have a work through these stages here and see if you can work out whether 51 is prime, 341 is prime, by Fermat's little theorem, not by any of the divisibility tests. Okay, pause and I'll come back to you. Okay, hope you got on okay with those. Hopefully you understood why I was leading you through these. We did a similar thing in yesterday's lesson where we were looking at something mod 50. We had to use power methods because we didn't have a prime number. 2 to the power of 8 mod 51, well, 2 to the power of 8 we've got above, that's equal to 256. And 256 mod 51. That's very convenient, isn't it? Because if I times that by 5, I've got 255. So that's congruent to 1 mod 51. So then 2 to the power of 48, did this kind of technique yesterday. 2 to the power of 48 is the same as 2 to the 8 all to the power of 6. So if we're checking out that mod 51, I know that 256, which is 2 to the power of 8, is congruent to 1, so I'll have 1 to the power of 6 mod 51. So that's going to be equal to 1 mod 51. And so then 2 to the power of 50, 2 to the power of 50 is 2 to the 8 to the power of 6 times by 2 squared. So that's going to be congruent to, well, I know that that is congruent to 1 mod 51. Oops. and then I've got the 2 squared, which is 4. So 2 to the power of 50 then is congruent to 4 mod 51. So it's not congruent to 1 mod 51. So 51 is not prime. And of course, I'm sure you knew, 3 times 17 is 51. So you knew before you started you weren't going to get that result of 1. And then 341, slightly larger. So, some of you may not know your primes up that high. Just a little hint beforehand. 3 times 341, that's equal to 1023, which very nicely, 2 to the power of 10 is actually equal to 1024 mod 341. So, of course, what we've got here is 1 above a multiple of 341, so that's congruent to 1 mod 341. So hence this one here, 2 to the power of 340. So I can say that 2 to the power of 340 is, well, let's just deal with the powers first. That's equal to 2 to the power of 10 all to the power of 34. So that means that 2 to the power of 340 mod 341 is congruent to 2 to the power of 10 all to the power of 34 mod 341. That bit there is congruent to 1, so that's congruent to 1 to the power of 34 mod 341. So it is congruent to 1 mod 341. Hey! It works. So is 341 prime? Yes. It seems to be prime. But actually it isn't. And the reason it isn't is because 341 is actually equal to 11 times by 31. So what's going on? Is Fermat's little theorem broken? Well, the key thing is the wording. It says if P is prime and you have that co-prime condition, then the power is congruent to 1 mod P. So the key phrasing is if that, then that. So P has to be a prime number and then it'll be congruent to 1. So it's not saying that you can get 1 for other values, for other powers. What we had here, we had a prime, yet we got it equal to 1. What we had there, we didn't have a prime, it was equal to 2 other numbers, but it doesn't work in the converse. So it's not saying that if you get that result, it is prime, it's saying only if P is prime, then you get that result. I mean, this doesn't happen too often, but it is known as a pseudo-prime when that happens. So it behaves as if it might be a prime, but then actually it isn't. So that's going to come up a little bit later, kind of officially in a definition. But to start with, let us do this proof. So the proof is based on this format here. So if P is prime, then A to the power of P is congruent to A mod P. And you'll be pleased to know that this proof we do by induction. So what we do is we prove by induction for different values of A. So the base case, when A is equal to 1, 1 to the power of P is congruent to 1 mod P. Yeah, that's correct. That is true. So now let's do the inductive step. So I am going to assume that this works for a particular result where a is equal to k. So k to the power of p is congruent to k mod p. And then, of course, what we need to do is we need to get a result for k plus 1 to the power of p. Now, hopefully that looks familiar. What we've got there is a bracket to a particular higher power. It looks very much like a binomial theorem. So the binomial theorem, of course, we were looking at last week in the context of number theory, but you've been doing it, of course, recently in normal maths as well. So k plus 1 to the power of p is equal to k to the power of p, and then I've got my first binomial coefficient p1, k to the power of p minus 1, times by 1. I'm not going to bother writing the ones. And then I've got p2, k to the power of p minus 2 times by 1 squared. Again, I know that they're not going to count. p3, k p to the power of p minus 3, and let's write the 1 before the end. P minus 1, k to the power of 1, and then the last one, well, okay, I'll have pp, I'll have k to the power of 0, and I'll have 1 to the power of p. So I will write that one there because that one actually counts. Now, of course, what we showed last week, what we realised last week, is that all of these binomial coefficients here, because I've got a prime value, all of these here are going to be divisible by p. So as p is prime, all these binomial coefficients are divisible by p. So if we look at that mod p then, so k plus 1 to the power of p mod p is congruent to k to the power of p plus 1 mod p. But if you look here, what was our assumption? Our assumption was that k to the power of p was congruent to k mod p. So this here is congruent to k plus 1 mod p. And what we've got there is the k plus 1th result. So our kth result, k to the power of p, is congruent to k mod p. Here I've got k plus 1 to the power of p, that's congruent to k plus 1 mod p. So our assumption was k to the p was congruent to k mod p. What we've just proved based on that assumption is k plus 1 to the p is congruent to k plus 1 mod p. So hence we have proved the k plus 1th result. And now we just need the final step. So the result is true for 1, and then we have proved that if it is true for a equals k is also true for a equals k plus 1. I am aware I'm getting very scribbly and you probably can't read it, but this is the dull but necessary, always necessary bit, so please always do it. Hence, by mathematical induction, the result is true for all positive integers a. It is actually also true for negative integers a, but positive integers a is kind of what that proof shows. Doesn't say in the specification specifically that you need to be able to do this. However, it does specifically state in the specification about the binomial theorem, you needing to know that. So I could easily, you know, see a case where they might put this on. Certainly a couple of years back, they put a particularly nasty kind of algebra, Fermat's last theorem combined with binomial theorem on. Wasn't the proof of it, but I think it could easily be there. Okay, so there's the proof. Let's look at a couple of more awkward examples. Again, dealing with divisibility. So here you can see that we're looking at this. Woo, it's number. It's got lots of 9s in it. That number there, we need to show that it's divisible by 13. Okay, well, show that it's divisible by 13. I guess an exam question would say, show by Fermat's little theorem that it is divisible by 13. So where's this 13 coming from? Well, if we count the number of digits here, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so what I've got here is 12-digit numbers, all with 9s in. So I can write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Crucially, as 10 to the power of 13, no, 10 to the power of 12 rather, minus 1. So that, of course, a 1 with 12 zeros, 13 digits, subtract 1 is going to get us to that number there. And now we can see we've got that being a prime and that 12 being 1 less than the prime. And I also know that the HCF of my base is 10, my prime is 13, is equal to 1. So I've got all the conditions there by to use Fermat's little theorem. So because of those two things there, we could say that hence by Fermat's little theorem, 10 to the power of 13 is congruent to 1 mod 13. Oh, sorry, I need to subtract 1 from that power. So 10 to the power of 13 minus 1 is congruent to 1 mod 13. And all we need to do here is just, you can rearrange that, can't you? You can just subtract that 1 from both sides. And of course, if something is congruent to 0, it means it's divisible. So I've got all the bits up there. I should just tidy it up a little bit. I'm afraid I'm going to write all that down again at the end. So 999, 999, 999, 999, which is equal to 10 squared minus 1. And that is congruent to 0 mod 13. And so hence, oh dear, it's coming up again. I maybe should have organised this better. Is divisible by 13. Okay, so there are quite a few of these kind of questions knocking about. It's particularly convenient because of all these powers of 10. So you might get one is divisible by 11, is divisible by 7, is divisible by 17. So those number of digits there should always tally, or be certainly 1 less than that. Okay, now, so officially then, these pseudo-primes, so this is something that you need to know about. This is something that's on the specification. So again, it kind of looks like Fermat's little theorem, but note we are using n, we are not using p. So what this says, if that you have two integers a and n, such that a to the power of n minus 1 is congruent to 1 mod n. So you've got that congruency to 1, but then if n itself isn't prime, then n is called a pseudo-prime to base a. Of course, it could just work with that specific one, so we talk about pseudo-prime to a particular base. So if you were to work it out, 2 to the power of 340 we already seen is congruent to 1 mod 341. However, if you work out 3 to the power of 340, it wouldn't necessarily be congruent to 1 mod 341. So it's just specific to a particular base. Show that 341 is a pseudo-prime to base 2. So it's the example that we did at the start, but this just is doing it in a bit more of an organised fashion. So we need to show two things. First of all, we need to show that it satisfies Fermat's little theorem with base 2. So we would write something like 2 to the power of 341 minus 1 is equal to 2 to the power of 340, and that is equal to 2 to the power of 10 all to the power of 34, and that is equal to 1024 to the power of 34, and that is congruent to 1 to the power of 34 mod 341. And what was it as 3 times by 341 is equal to 1023. So that is equal to 1 mod 341. So that satisfies Fermat's little theorem. So satisfies little theorem, but we then need to show that it isn't actually prime. There's going to be some, I know there's some button, isn't there? To find, I know there is, you've kind of showed me, but I just happen to know, of course, because I've checked this out, that it's divisible by 11. 11 times by 31 gets us 341. And what do you mean I happen to know? We did it at the very start, didn't we, just a few minutes ago. So I know that 341 is equal to 11 times by 31. Hence 341 is not prime. And so 341 is a pseudo-prime. Okay, that word, pseudo-prime, is given in the specification, so you could well be asked a question like that, so you need to know the definition of that.